Welcome again, everybody. This is our video solution to problem 5 from quiz 11. This is in spring 2023, Math 302 at Cal State Fullerton. And this is the last problem on the quiz. This is again going to be about equivalence relations, but this time we'll also talk about quotient sets, transversals, equivalence classes, etc., etc. All right, so what we have here is a list of statements. These statements could be true, they could be false, and we want to figure out which ones of these are always true. I'll tell you right now that there are some true statements in this list, and the ones that are false are essentially duplications of incorrect student work over the years. So take a look out for things that you might have written down, and hopefully we'll be able to clear up some misconceptions. So the first statement, the quotient set S mod E. So, right, what are S and E here? That's right, so it tells us up at the top that S is some non-empty set. Okay. And E is an equivalence relation on S. All right, now pictorially, what are we talking about here? So I might have a set S, which I'll maybe draw with a rectangle here. And inside S, I have some points. Okay, these are elements of the set S. And E is an equivalence relation, and we were able to show in class that an equivalence relation always induces a partition on the set. So a partition means I can break this set up in some way so that every dot lies in one of these subsets we get from this partition, and only one, right? So it shows up in one, but it doesn't show up in more than one. So we have partitioned the set S, in this case, into 6 different parts or equivalence classes. Okay. This question is asking about quotient sets and transversals. So let's first, what is a transversal? A transversal is where I would go through and I would just pick, right? I'll pick one element from each equivalence class. Okay, so there's one. Now here I have 3 choices. Doesn't matter. I'll pick this one, and maybe this one, and this one, this one, and this one. Okay, so I pick one from each. Okay, so a transversal contains one element from each equivalence class. Okay, so that's what the blue bit is. Okay, now if I look at the entirety of each of these parts, that is the equivalence class. So let me do those here in yellow. All right, so that's an equivalence class. That's an equivalence class. That's an equivalence class, and that's an equivalence class. So these yellows, that represents the equivalence classes. And what you can count off, right, is that there are 1, 2, 3, 4, 5, 6 equivalence classes. And I could even give names to these things, right? Okay, maybe I'll call this like E1 and E2 and E3, and then E4 and E5 and E6. So those would be all of the equivalence classes. And so now when I want to build the quotient set, what am I talking about? The quotient set will be the set of all of the equivalence classes. So S modulo E, this is the quotient set, is going to, in this case, contain as its elements the equivalence classes. So note, the quotient set does not contain the dots. It only contains the set of dots, right? Each set of these dots, right? And there's 6 of these little subsets, right? That give you dots of S. Okay. And of course, I know if I took the union of all of these things, I would get S itself. Okay, but the quotient set doesn't see the elements. It only sees the equivalence classes, right? Those are its elements. So the transversal are elements, the equivalence classes are sets of elements, and the quotient set contains equivalence classes. So it contains sets of elements, not elements. And so this statement that the quotient set contains a transversal of S, well, that would mean it would contain elements of S, but it doesn't. It contains sets of elements of S. So this statement is false. All right, how about B? Every equivalence class is a set of representatives of S with respect to E. All right, so what is a set of representatives? Well, actually, a set of representatives is just another name for transversal. So this equals set of representatives. So if we're saying every equivalence class, so like E1, that's an equivalence class, is a set of representatives, no, a set of representatives would be a transversal. That would be a set where you take one from each. So this statement is also false. All right, part C, every transversal, okay, we have a transversal here, contains exactly one element from each equivalence class of S with respect to E. And yeah, that's exactly what a transversal is. It contains one element from each equivalence class. So yeah, so this one is true. All right, D, if X and Y are in S such that, okay, now what did this square bracket mean? Well, let's say I gave a name to this element up here. Maybe I called it X. Then, or actually, let's do it in the second one here in E2. If I called that one X, then the E2, another way I could write E2 is square bracket X. This is the equivalence class of X. Of course, if I had chosen another point, like Y in here, this would also be the equivalence class of Y. Okay, well, here you have an equivalence class E2 that has X and Y in it, but it has other stuff, right? There's a third element. And this statement is saying that if the equivalence class of X and Y are the same, then the equivalence class of X is simply equal to the elements X and Y. Well, that's clearly false here. All right, E, if S is infinite, all right, so our picture is no longer a good picture, then the quotient S mod E is also infinite. Well, here's where a good example would help us. So there's an infinite set, Z, and we worked with an equivalence relation, which we denoted by 2Z. So the equivalence relation, right, was defined that X and Y are in the equivalence relation if X minus Y is a multiple of 2, right? Alternatively, X is congruent to Y modulo 2. So this gave us an equivalence relation, and then the quotient set was Z mod 2Z, and Z mod 2Z we know has only two equivalence classes, the class of 0 and the class of 1. Okay, so here's an example where you have an infinite set, but a finite quotient set. So E is also false. All right, well, what about an infinite set and the quotient set is finite? I mean, we have an example of that. Can we get an example where the quotient set is infinite? Well, what if I define a new equivalence relation, also on Z, so that's a nice infinite set, but now we're going to say that X and Y are equivalent if the absolute value of X is equal to the absolute value of Y. Okay, so this happens if and only if Y is either equal to X or is the negation of X. Well, if we do this, then the equivalence classes, so here I would have Z mod, well, I can just use E. I could have written E up here as well, right? But by convention, we write 2Z. So Z mod E, what is that going to have in it? Well, let's see. You have the class of 0. In fact, that's the only thing in that class, right, is 0, because it's the only thing with absolute value 0. Then you have the class of 1, which is going to contain plus minus 1. And then you have the class of 2, which is going to contain plus minus 2, and so forth. So in fact, this is going to give you an equivalence class for every non-negative integer. This is certainly an infinite number of equivalence classes. So just because you have an infinite set, it doesn't mean that the quotient set has to be finite, right? Or infinite. You can have both. So this statement is also false. All right, G, if X is an element of the set, then the equivalence class of X, all right, let's go up and look at our picture again. There we go, I have an X. The equivalence class of X, denoted with square brackets, yep, sure enough, that's what we do, consists of all elements Y, such that X and Y have the property that they're pairs in the equivalence relation. Oh, yeah, that's actually what makes the equivalence class up, right? It's all the things equivalent to X. So yes, this is a true statement. That's just our definition. All right, and finally, H. One can find a transversal of S. Okay, remember that's where we choose one from each class. We can find a transversal with respect to E by choosing a single element. Oh, that sounds good. A single element of S. Oh, wait, a single element of S. Like E1, that point in there in E1, and finding its equivalence class. Oh no. I choose a point, I take its equivalence class. That would give me E1, for example, or I could choose Y, and that would give me E2. But I need a transversal. I need one point from every equivalence class. Yeah, this doesn't work. So this is a false statement. All right. I hope through looking at this thing carefully, looking at this picture again, that this is going to help you start to internalize these definitions a little bit more. This idea of equivalence relation, transversal, quotient set is absolutely ubiquitous in mathematics, one of the most important ideas that you can learn. So yeah, keep working on it, right? Let's get this thing done. All right, we'll see everybody next time.